Hello everyone, welcome back. This is a continuation of the performance engineering case study 1.0. So wherein we were analyzing the book vaccine API. So initially we tested this API with a single user and response time was around 1 second, which was okay. But as we increased the number of users to 10, we observed that response time was degraded. Then what we did, as per our theory, so whenever there is a degradation in the response time due to an increase in the user load, it must be due to contention. So we suspected that there may be a thread blocks or thread must be waiting for some resources. That's why response times went high with the increase in the user load. So with that observation, so we took a thread dump, and when we started analyzing the status of the threads, most of the threads were in blocked status. Okay, so that's where actually we stopped our session, and in this session we will continue with the further analysis to see how exactly threads got blocked, and what exactly is the root cause. Can you mitigate this, or can we reduce the amount of blockages, and so on and so forth. Okay, so we'll test with 10 users now. Okay, it is 10 users. Yeah, I think test is still on. Okay, so we can analyze. Okay, that's why I think response time is also around 3.5 seconds now. Okay, so this is the glow root. Basically it is a open source APM tool which can be used to monitor Java applications. So if I am not wrong, this is the API book vaccine. Yeah, book vaccine is the endpoint. This is the API under analysis. Okay, so we can go to a thread profile, and we can see what is the status of the thread. Okay, if you see here, yes, status of the thread is blocked. Okay, where it is blocked on book vaccine slot in PE controller. Okay, so if I go here, so this is the book vaccine and this is the book vaccine slot. Okay, here we can see synchronized block. Okay, so we have a few lines of code in the synchronized block. Oh God, okay, here we have a thread dot sleep. So as we know, synchronized block is a feature in Java which allows the piece of code to be executed se- in a sequential manner. So you do execute this piece of code with 10 threads. A moment control comes to this particular block, it becomes sequential. So that's how updates to the shared resource should happen, right? Okay, so synchronized section help us to implement that particular feature. So here we have a thread dot slave. So what happens when I test with single user? So control comes here. So it waits for around 900 milliseconds. Again, it comes back and it continuously execute this code. Okay, so we can see around 1 second is the response time. When I start with two users, otherwise when I start with five users, what happens? The five threads are trying to execute this code at the same time, almost same time. But moment it comes to this line of code, what happens? It should become sequential. Okay, it has to be one after another. Let us say five threads are trying to execute this code at the same time, and the first thread get into the synchronized block. Okay, so what happens here? So because of thread dot sleep, it thread dot sleep, thread one will be waiting here for a almost 900 milliseconds. Okay, so till that point of time, second thread has to wait simply at this section or at this line of the code. Okay, so when we increase the number of thread, then what happens? The amount of thread that waits for this particular section to execute will be more. So that's why we see increase in the response time as we increase the number of users. So if you want to understand a little bit in a uh, outside our IT, outside our software. So I think here I am trying to explain similar kind of situation using uh, in a running track. Okay. So let us assume we have a runner. Okay. This is the case number one. We have a runner here, and this is the source, and this is the destination. He has to run from the point one to point source to point destination. So let us assume he needs 10 minutes to reach from source to destination. Since there is no any obstacles, definitely he can run year to year, and he can reach this destination within 10 minutes. Let us see, this is case number two, by the way, it's a type of mistake. There are 9 runners out there now, and 9 separate dedicated running tracks we have. Okay, and condition here is each track is dedicated, and for example, if runner one is there, so he can only run in this track. He cannot go to this track, or runner two cannot come to this track. That is the condition here. So in this case, what happens? Though we have 9 runners or even 90 runners, as long as we have these kind of dedicated tracks, okay, so they can run at the same speed. Again, one more thing is here, these are all, I mean, these runners are identical runners. Okay, they are identical from all perspective, height, weight, and efficiency, whatever you call, okay, endurance. So there are these runners are identical, and that they can reach from year to year within 10 minutes. There is no doubt about it. Even not only 9 runners, even if we have 90 runners also, or 9,000 runners also, as long as they are identical and they have a dedicated track, okay, they can reach from source to destination within the same time. Now, okay, let us go to another case. This is case number 3. Okay, so here there are 3 sets of tracks are there now. Okay, now what happens from here to this to destination is same, source and destination, the length is same, and here uh, these runners you have dedicated track only till this point. Okay, moment they reach here, okay, with reach here, they have to use this tunnel to cross this particular border and can reach this dedicated track again. I'll repeat again. So runner one and all the runners can run in their dedicated track until this point. Once they reach this point, so beyond this, there's no dedicated track here. Okay. Since I said only one runner can run in a track at the same time, that's how these tracks are designed. Okay. So what happens? What happens now? Let us say when all the nine runners are running here, and approximately they reach this point at the same time. There may be a difference in microsecond, though they are identical, like our threads. Okay. So what happens? Whichever runner reaches first here can get into this tunnel, and he can finish this portion and can go to his own track. For example, runner one comes here, he get into this tunnel. Okay, after this, he goes to this tunnel, this track again. Same runner, runner two, runner three, runner four, and other runners as well. So in this case, also, do we think these runners can run from source to destination in 10 minutes? No, absolutely no. Because what happens once they reach this stage, or once they reach this point, since it has to be sequential, all the other runners should wait till the runner who reaches first here completes running this particular portion. So that's why it cannot be 10 minutes. It should be more than 10 minutes. What happens again, as we increase the number of runners, amount of runners that waits at this point also increases, which in turn increases overall running time. I hope I try to explain what exactly is happening in synchronization block here. Okay, suppose if we keep this synchronization sleep, okay, this sleep outside the synchronized code, then response time should not be at least 9 second or 10 second with for 10 users. Okay. So that is the point here. Okay. I think it is very straightforward, and I don't think it requires some kind of a demonstration. By the way, thank you for watching this video. And if you have any questions, please post your questions in the comment section. Thank you.